Again to my channel. I want to complete the tutorial on basic electronics components. Last time we talked about resistors, voltage dividers. So let's just do a simple review. I mentioned to you last time that a resistor could be used as a voltage divider. So let's just run that test one more time and just get familiar once again with that. So I have two resistors in series. And let's get a voltage source, right? So we need a DC voltage source, and let's just connect this together. The two resistors are in series, and then we connect the power supply. All right, so let's just put a switch. Why not? Single pole, single throw switch. Put it right there so we can, let's toggle it on. All right, it's trying to zoom it. It's coming into big, so let's just reduce a little bit. Okay, maybe a little bit more so it can fit on the screen. All right, so we have the resistor set up here. Let's um just do some voltage current analysis, right? So in the middle. So according to what I said last time, since the resistors are in series and they're the same values, the voltage developed across each will be the same. So we're gonna do this again. So we already know this is 12 volts, right? So but we're just gonna put another annotation right there, just to verify that the value in the middle here will be half the value here. All right, so let's run the simulation, and we're getting something weird. Current is 6 milliamps and voltage is 2.4. It looks like is a negative value. Can you tell why this is? Yeah, okay, let's try to put a ground to this. We're expecting at least 6 volts here because it should be half. All right, so let's put a ground here. All right, because the reference for the voltage meter is the ground. So now that we have it in place, let's run the simulation again. Now you see there's 12 volts and 6 volts. So the resistor acted as a voltage divider. It doesn't really matter the value of these resistors. Doesn't matter as long as they're the same, it will be a voltage divider. So let's increase the value of this resistor by 10. So it's 10k. Automatically the voltage developed across these jumps 10. That's 10.909. So the remaining 1.1 is developed across this resistor here. How about if we increase this value also by 10? Automatically the value is restored. So how about if you increase this even further by another 10, right? So make it 100k. So obviously there's gonna be 10 volts, 10.9 volts here, and then 1.1 volt down there. Let's see. Yeah, so um 1.0109, so 1.1 volt down here, and then over here will be developed the remaining voltage. So this is what we demonstrated last time, so this is kind of just a revision for us. I'm gonna stop this simulation. So today let's go a little bit further. I'm gonna just take this out of view and let's look at a variable resistors, right? I'm gonna take this value here and just flip it around a little bit. Okay, so if I want to create voltage divider effect right here, I can do the same. Let's get power supply here. Again, DC voltage. Connect this here and connect this down there. And if you want, you can put a switch, but we don't need it. You know what the sorry, I'm gonna connect this differently instead. I'm gonna connect it here. Okay, so let's see, and let's do our analysis again. Voltage current here. Okay, let's no let's put it in a better position. Yeah, make sure there's connection. And our reference, zero reference is also ground. Let's run it. All right, so 12 volts over here, and the value is, so this is on 50% mark. So what do you think the voltage at the middle of this is? So it's 50%, but this portion is not grounded, it's not connected to anything. So let's see. If I connect this to ground, and if I want to run any good analysis, if I put the meter here, it's to ground, so you don't get anything. There's no other way to test this. So what we're gonna do is to change this configuration just slightly by adding one more resistor. You're gonna see why shortly. So because we want to be able to measure across a value, so let's add a resistor here. All right, and then we'll close the circuit again. So this time around, we can test the value in the middle where they connect. So right here, we can verify the value here. So this resistor is 10K. Why don't we make that value 10K as well? Let's get this higher a little bit. All right, let's make this value 10K as well. All right, so you have 10K and this is at 50%, which means basically this is 5K, right? So let's run the simulation. So 12 volts top there, 4 volts right here. So this is half of this value, right? So the voltage across here is also going to be half that. If I remove this, let's delete that connection. Let's delete this connection and see and run the same simulation again. What do you think the value will be? It's the same, right? But now let's change the value. Let's change this percentage. Let's increase this and see what the value will be. Let's increase this to 90 or 100%. Now is half of the total value. So this value is 10K, and that value is 10K. So there's this voltage divider. Now you can see, let's use this slider to see what happens to the voltage here. If you build amplifiers, which we might look at later, you realize that the volume control, actually the volume control is made from a potentiometer, a variable resistor in this format. So as you turn the volume, you're actually changing the value of the resistor, and as you do, the preamplifier section that is connected to this position of this voltage current analyzer, if a multimeter in practical sense, the voltage is dropping or increasing depending on the value, right? So you have a voltage division going on here. This portion represents your audio source, maybe auxiliary source, and this is your volume control, and this VA represents the signal seen by your preamplifier stage, right? So, or the amplifier state, depending on the type of amplifier you have. So as you change the value, so let's change the value again. Let's just slide it. You see the voltage changes, varies. As the value approaches 0%, you have almost no voltage going through, 1.2 microvolt. And as you slide, so this is one way of using a voltage, a variable resistor. All right, there are other forms of resistors. There's light or photosensitive resistor or light dependent resistors, LDRs. So the value change with the intensity of light. All right. So let's see if we have that component here, we can demonstrate that. So let's look at resistors. We don't have that here, but we're going to build some circuits later with light dependent resistors, and I'm going to refer you to this. But just think about it as the value changes, as the light intensity changes, the value changes. All right. So look at okay. I guess I need to show this again. Not only is the value of the resistor changing, as you can see, not only is the value of the resistor changing, the percentage of resistance changing, but what also is changing is the voltage that is developed across it. So that's what we have demonstrated here. All right, good job. So change the values and play around with it, see what you can find. That is it about resistors. Mostly we can look at other forms of resistors. Later there are a couple of other types that you can see here: impedance block and then voltage control resistors, and so on and so forth. But the basic principle is that resistors can be used to provide voltage division, and a resistor is a component that resists the flow of electric current. So you have to be in real sense when you design a circuit, you have to be very careful the value of resistor you use because the current developed across them. So let's run this one more time. You can see the current developed across this resistor. Um, Across the circuit is going to be the same value because they're in series. So it's about 8 824 microamps. So about um, zero point 0.8 milliamp, right? So and power is I squared R. So when you multiply this value squared times the R, that's the power going through this resistor. Make sure that the resistor can sustain such amount of power going through it, otherwise something could go wrong. So let's reduce the value here to increase the current. 1K here. How about this one? Let's reduce it also, make it 1K, and the current increases as we did that. So if you're using 1K resistor, that's more current. Then do the calculation. I squared R will give you the power developed across it. So you can take the right amount of resistor that can withstand the current or the power developed across it. Okay, so let's look at other components. Capacitors. Okay. Um. So this here we have transistors and so on, diodes, op amps, resistors. Okay, there are capacitors. All right. So what is a capacitor? In a nutshell, a capacitor is a component that stores electric current. So remember how we say that when a resistor is in series, the value increases. In a capacitor, when they're in series, the value reduces, but when they're in parallel, the value increases. So the value of this capacitor, this combination, is 2 microfarads. The value of, if I do it differently, if I have it this way, the value of this combination of capacitors is 0.5 microfarads. Likewise, for a resistor, the value of these resistors is 500 ohms, so 0.5 kilo ohms. In the same vein, just like we talked about, the value of this resistor is 2 kilo ohms. And the formula, let's see if we can add a note so we can talk about the formula for resistors and capacitors. We talked about resistors in details, but I realized that we can just go high level, very high level, just state the formulas. Let's see if we can add a note. For resistors, R is equal to resistors in series. R equivalent, let's just say R equivalent Okay, let's just use EQ, you understand, is equal to R1 plus R2 plus all the way to Rn, where Rn is the last in the series. This is for series. But for capacitors, okay, let's finish resistors. So resistors equivalent for resistors in parallel is R equivalent is 1 over. So I'm just gonna do this way. 1 over divided by R1 plus R2 plus all the way to Rn. This is parallel. And the converse is the case for capacitors, so you don't even need to write it again. For capacitors, it will be capacitors in series, so cap equivalent, C equivalent. So we're going to do series first. So it will just be the same as this. So capacitors in series will be C1 plus C2 all the way to Cn when they are in series. But when they're in parallel, when capacitors are in parallel, the value is just the addition of all the values in that parallel combination. Alright, so this is just the simple um, formulas you need to know about capacitors and resistors. Alright, very, 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 very simple. Alright, so let's continue. Alright, we're gonna go back to this section. So, anyways, that is all you need to know about capacitor for now. So the uses, what are the uses? You use capacitors for filtrations, for coupling. If you want to couple two circuits that have different power supplies, you want to use a capacitor to couple them so you can isolate the DC conditions of both circuits while coupling the signal. So we look at a capacitor as a DC open and an AC short. So think about it that way. When a capacitor sees DC voltage, it is an open circuit. It doesn't let it go through. But when it is um, an alternating current, it lets it go through because the capacitor will charge and discharge as the voltage changes in amplitude. So when it's positive going, it charges, and then when it's negative going, it discharges and back again. But when you use DC voltage, once it charges once and the voltage doesn't change, it stays charged and then doesn't let any further voltage or current to go through. Sometimes DC voltage can go through during power up. So that's why capacitors are used as power up on shots, because the voltage starts from zero and then all of a sudden gets to the VCC, and there's a jitter between that zero and the value. By the time it settles down, there's a jitter. So that moment it will allow some voltage and current to go through, and just shortly after that, it shuts. So but in a general sense, just see it as capacitor is an AC open, sorry, a DC open and an AC short circuit. So in other words, it allows AC to go through, but it doesn't allow DC to go through. It's a DC blocker, right? So we're gonna see combine this in a circuit shortly, but let's introduce the rest of the components. The other thing we're gonna talk about is a diode. So we can always go back. There's no particular, formula doing this, but I just want to make sure we get through all the basic components in one or two videos versus making it in multiple videos. You can always come back for questions and I'll make more videos for you. What is a diode? So a diode is a component, electronic component that allows voltage and current to flow only in one direction. Um, and although there's sometimes you have a reverse voltage, but it's it's a limited current or voltage that go through in the reverse direction. Just look at this as a funnel. Normally, a funnel will allow, if this is a funnel and you pour water from here, it's better. It looks better for water to flow from top down versus from down up. Let's just flip it around. Let's flip it um, this way. If I'm pouring water from the top, maybe if you can get into the funnel, but I'll be losing a lot of it. So it blocks voltage or current from flowing up top down, but it allows it easy. Why don't I make a copy of this so I don't have to flip it all the time? Let's make a copy and flip the copy so we can look at the copy separately. All right. So D1, if my voltage source is from this top, then D1 will allow voltage to go through more versus D2. Right, just makes sense. So this is just if you use this for filtering, for rectification, not filtering, sorry, for rectification, use capacitor for filtering. Okay, so when you have an AC circuit and you wanna, let's take an AC voltage source. We have one here, AC voltage source. So if we take an AC voltage source here and we connect it to this diode. So when the current is positive going, current will flow through here. But when it's negative going, it will block it. In other words, when it's negative going, it means the current is actually flowing backwards, or the voltage is going backwards. So this will block it, but it will allow it to go the other way around. We can test this. We can see that this works by just adding two more components, and we'll test it. So let's do that. Let's add one more diode. This diode is a special kind of diode. It's called light emitting diode. And for the simple reason that it emits light when current flows through it. So let's just try it. Right, so we're gonna add a switch here because we might want to interrupt this from time to time. Single pole, single throw again. Since we just have a simple circuit, so let's close the switch. And let's have our ground. We've learned from the previous video we need a ground, okay? Of the previous section, we need a ground. Of course, now you know that I was doing other things earlier, but it's fine. All right. So I start my simulator now, and I have only 1 volt here. Nothing is happening. So why don't I increase the voltage? So let's increase the voltage. But I might blow my my diode. So why don't I put a resistor? Why not? Why not? Why not? So let's move this a little bit, and we can put a resistor anywhere, but let's just do it this way. Okay, let's make it clean. Let's make it clean. Let's put a resistor. I think we have some resistors already, but grab one more resistor. Alright, so let's run this simulation again. I know that I haven't changed the value of the voltage, but I want to do it while the simulation is running out so we can get the value. So let's just take the voltage here. So the LED is off, so let's increase the voltage just gradually until we can get the LED to light on. There's a particular threshold beyond which we can light up the diode. We don't really need 2 diodes, to be frank. We can use only LED to perform this experiment. So at 6 volts, this is not lighting up. So could it be something is wrong? Let's see. How many volts do we have? Oh, I don't have the ground. Remember, we need a ground. All right. I believe this should light up. Okay. So it lights up. Can you see that? All right. So we're gonna do this experiment one more time. Let's go back and find out the threshold. it's still lighting up here. You can notice flickering red. 3.5 volts, very low. Yeah, very low. 2.6, very low. 2.1, very low. 1.8, you hardly notice anything. So as we increase, the brightness increases. So you gotta be careful. This is a simulation. In real life, you might go beyond a point and your diode will go off or go bad. The frequency is pretty high, so it's hard for us to see. So why don't we reduce the frequency from 1 kilohertz, make it 100 hertz? How about 10 hertz? So it stays on a little bit. How about 1 hertz? So once goes on once a second. Let's keep going low and low and low and see how low we can go. Okay, so at 10 microhertz, it stays on for a little bit longer. You can keep going as low as you want to go, but as long as it stays on, the same amount of time is going to stay off. So it's important to know that if you're going to do this. Anyways, so at this point, I guess can you notice that it's coming? It's coming because it's a an AC signal, so it goes from very small amount, keeps climbing towards the maximum, and then gradually from the maximum goes down to 0 and then goes to negative and then comes back around up. So let's put it to where we can see it quickly and do our other experiments. All right, so 10 hertz, yeah, that's good. Now let's increase the voltage a little bit more. This is a lot more, 63 volts. So let's just go a little bit. Now, so the experiment I want to do, that's why I have this here, is to, what if I put this diode in that position? So let's see. So, all right, doesn't matter. I think we interrupted the simulation while it was on, so that's why it stays on. But anyways, we're gonna stop it and or maybe I put it in pause when it was on. Sorry, I think I paused it when it was in on. Yeah, so it stays on. So we needed to stop, not pause. But anyways, so let me replace the value without making any other changes. Remove this value here and then replace it with this. All other things remaining the same. Then let's run the simulation one more time. Now it stays off and doesn't come on. Why? Because this is blocking the flow. When it is positive going, the signal wants to go this way, but it's blocked. When it is negative going, the signal wants to go this other way and it's also blocked. So we are going to verify this. We're going to verify this shortly. But let me show you something here. Let's try to increase this voltage. Let's just go a little bit higher, a lot higher. Sorry, not just a little bit, but a lot higher, and see what can happen. Well, this is simulation, but I expect this to yeah. So you see it has crossed. Now I've broken the system because I have surpassed the reverse um, voltage limit for this diode, and it's broken down, and the voltage is flowing the other way around. And I think this voltage is too high for even this other diode, and everything is smelling right now. If you are inside this computer, you will be smelling this. I'm just kidding, but if it's in real life and you have this amount of voltage, something will be smelling quickly. Anyways, let's go back and see if we can recover our system. All right, so the system is recovered now. Let's go crazy one more time before we stop this simulation. Uh, don't do this in real life. don't do it in real life, because the amount of voltage, 6.6 megavolts, 66 megavolts, 660 megavolts. Where are you going to find that kind of voltage? Gigavolts. And now I'm broken the system. Everything's going to smell now. If you can see this, the whole circuit is smelling. Yeah, it's smelling. Don't do that. All right, so let's go back and prove our other concept. I think you've understood what I'm trying to show here. Diodes conduct only in one direction, but you can go crazy if you want, and you force it to go the other way around. Just know it will. If you surpass the reverse bias voltage, you're going to break your system. Okay, let's remove this. This is a diode, so we don't really need another diode to help it out. I just use that diode to demonstrate something. So let me show you the other crazy thing we're going to do. Not really crazy, just to demonstrate, the flow, because I was telling you that the voltage, um, when it's positive going, this happens. When it's negative going, that happens. You might be wondering what you're talking about. So let's demonstrate this. So to tell you, when this signal is positive here, this diode will conduct. So the current will flow from the anode to the cathode. The cathode is the side that looks like a K is on it. So it goes from anode to cathode. And then when it is negative going, the flow will go the other way around. So when it's negative going, this portion is positive going. So let's run the simulation. You will notice something about the two LEDs. Just watch LED 1 and LED 2. Let's move them. Okay, yeah, let's keep them side by side, doesn't matter. All right, watch the simulation right now and tell me what you can find out. Did you notice that? When this is on, this is off. When this is off, this is on. So let's change the frequency a little bit to make it easier. One of them is gonna stay on longer and one off longer. That way, can you see that? Alternating. So whenever one is positive, the other is negative. That tells you that the voltage is reversing. Of course, you know that is an AC voltage, but what it tells you is that the diode only allows the flow in one direction. Okay. And I understand that this configuration might be a little bit confusing, because this might flow this way, but there's no potential drop this way, so this voltage cannot flow back up. It's the voltage here is higher than the voltage there, so it wouldn't flow back up. But if you just for clarity, to avoid questions or to minimize the confusion, I'm gonna do this way. All right. So we have the same value here. Okay, we're gonna run it again. Now, if you're doing this in real life, and you have two values this way, two values. If you want to connect these resistors here, just make sure that the value of the resistor is. Anyways, in this circumstance, when one is turned on before the other, it doesn't really matter. But if they have a chance of being on at the same time, we want to protect them and separate them this way. But anyway, so this is what we want to demonstrate here. So let's go quickly to other things. I think we've covered a lot today. Looked at resistors, we looked at capacitors, we looked at diodes. So let's look at transistors. So I am not telling you everything about these components. I'm just introducing them. There's a lot of details about this. I'm working on a book. It's a book I previously wrote in 2004. I haven't published this book because other things overtook the event. There was a time I was teaching at a university as a private. I was conducting a private tutorial for the students in the university, and I was teaching them electronics designs. And at the end of the period, I realized how much materials I've given the students. It was a lot. About 80 leaves exercise book was filled with the materials that I was, the information I was giving the students, and I felt compelled to turn it into a textbook because it was just so rich information I had there. And I had converted it to a textbook um, just before I left the country and traveled overseas. And the rest is history. Things happened and I didn't get back to it. I still have the manuscript, so I'm cleaning it up because I wrote it just basically from the class perspective, from the tutorial we were conducting from that perspective. Um, and I felt that I probably should or could add something more, just clean it up a little bit so it doesn't just it's not just the notes that we collected from the class. And so I'm working on finalizing that book, and it will contain all this information I'm sharing with you guys right here. So watch out for that, and you can get all the details about the design we're working on right now. So um, what is a transistor? A transistor, just look at it as an electronic switch. It's an electronic switch. You know, you have so many definitions about a transistor. It can be an amplifier and so on and so forth. But right now, just look at it as an electronic switch or a tap. You know, a tap, we have the inlet and the outlet, but there's a valve that control the flow. So for this transistor, this is an NPN transistor. Let me see if I can zoom it a little bit to show you something. When you have a transistor this way, there are three terminals. There's the emitter, collector, and the base. Emitter, collector, and the base. I'm going to tell you, you know, all this. I'll give you all the information so you know how to identify them. But just right now, just know that transistors have emitters, collectors, and bases. This BJP, bipolar junction transistors, BJTs. There's MOSFETs, transistors, there's JFETs, junction field effects, and metallic oxide field effects, and so on and so forth. However, there are there are three terminals to most of these transistors, and I want to show you how to identify them. So this, what we have here is an NPN transistor, and I'm going to tell you the other one is a PNP. Right now, when you're picking it, you see NPN and PNP, but let's just pick a PNP, and we can look at. Okay, I have 20 I have the limit of components I can put on this circuit. So I'm going to delete some of them so I can add more components. So let's delete some of the components. We are done with some of them, so we don't really need them to be here any longer. So we can get rid of this entire section. How about make it smaller? Select all and just get rid of them. Okay. I'm not able to select all. Let's get rid of the things we're done with. I was gonna just have a screenshot of everything at the end, but there's no point this time. So let's do. I'm using a free version of this software. So PNP. All right. Let's look in detail and see the difference between the two. You can see they look similar, but if when you look closely at one of the terminals, can you look? This one has an arrow. This arrow is going out. This one has an arrow. The arrow is going in. So if it's going in, it's pointing in. If it's going out, it's pointing out. No, this doesn't solve my problem. The problem I want to solve here is to help you identify how to know when it's an NPN transistor or a PNP transistor. So what I used for my students in those days is I said, make sure the two transistors are arranged in the same way. In other words, the arrow is on the portion that is facing the ground, the bottom part of your page. So if this area is the bottom part of my page, I can tell you these transistors, I have both arrows on the lower side of my page, not on the top side of the page, but on the lower side of the page. When you do that, just put a marker, use a pen to draw at the bottom, at the left side, the left. If you put an arrow down on the left and you also put an arrow down on this side, any of them that spells an N is the NPN transistor. So when you put an arrow, you get something that looks like an N, the letter N. So the transistors, one of them look like a V coming out, and the other one look um, like yeah, like an exponential sign this way. So if I put a 1 or a stroke by this one, it doesn't look like an N because it will look like this, that, and this. No, where is it? Yeah. So the one that looks, so look at this one. It looks, one of them looks like it's going up, which is this one here, and the other one looks like a V, which is this one here. So I'm just gonna put a straight line on the left of each one. Anyone that looks like an N is my NPN. So this one here looks like an N. So it's my NPN. This one here does not look like an N. So obviously it is my PNP. Therefore, it is PNP. So this one looks like an N. Therefore, it is NPN. Okay. So it's a simple test, but you get it drift. You can use any other method to tell. With time, you don't need this kind of method. You see it, you know. Or when you're picking it up, you know. But this is a quick sign. Now, I'm gonna show you in when we start doing some practical sessions. I will show you um, how to test for the emitter, collector, and the base. But for now, just know that you have where the arrow is your emitter. Where the arrow is your emitter. The opposite side, the other side of it is the collector, and your valve is your base. So I'm gonna get rid of the PNP transistor, and we're gonna do a little bit of experiment with the NPN transistor. So NPN. So in this case, for NPN transistors, the collector is positive with respect to the base, and the base is positive with respect to the emitter. So it goes from top to bottom. Most positive, more positive, and positive or negative. So negative, less negative, more negative. So more most negative. So this is negative, more negative. Sorry, this is negative, less negative, least negative. And if you go the other way around, it's positive, less positive, least positive. So the base to have this transistor in a forward bias configuration, the base must be positive with respect to the emitter, and the base and the collector will be positive with respect to both of them. Now let's just run this simulation and see if we can get this diode to turn on. Before we do that, we're gonna add a little bit, maybe one more component. Let's add one resistor here. All right, so I need to create more room. All right, let's run the simulation and see what's going on here. So we run this and the LED is looking at us. It's not doing nothing. We have just 1 kilo ohm resistor here and an LED at 12 volts, but it's not doing anything. Why? Okay. Do you know why? Let's see. Let's move this resistor a little bit. We don't need this resistor up here. Okay, I'm gonna move this resistor a little bit. And then I'm gonna put an analysis point here. So let's do some analysis at this point. Then run it again. So R is not connected. R7 is not connected. Where's my R7? Okay, anyways, we don't need that R7. It's a previous circuit. But right here, the LED is still off and the voltage here is 11.7 volts. Almost the whole voltage is here. but the current is almost non-existent. Current is not flowing. This transistor is supposed to be my current amplifier, but it's doing nothing. Why? Well, remember I said the transistor is an electronic switch. So let's introduce a switch. So we can talk about a switch. So we have to introduce a switch. I will just close the circuit. Okay, we can run the simulation, and we'll see. Well, it does seem that the voltage is pretty high, but the current is non-existent. Where is the voltage coming from? Anyways, this is a phantom voltage. So let's close the switch. We close the switch, still nothing. All right, so let's do something more. Now you already know that this resistor is hanging here and it's doing nothing for us so far. So why don't we just make a connection? But I need a switch. I need another switch so we can turn it off and on, right? You get that? Cool. So let's put this switch here, and then we connect the base of this. Okay, let's open the switch and then run the simulation. All right, so you can see still nothing is happening. The voltage still high, currents micro level current. So let's close the switch now. Whoa, did you see that? The LED comes and the current jumps high, and the voltage here is very small. This voltage is 28 millivolts. 28 millivolts. This is the voltage across. This is the VCE voltage from the collector to the emitter is about 28 millivolts. The rest of the voltage, the rest of this 12 volts is developed across this diode and this resistor. And the current flowing 11 milliamp, 11 milliamp is flowing through this system. So make sure when you use this transistor like this, the IC of the transistor must be higher or equivalent to this total current flowing. So this is a electronic switch. Let's turn off the switch. The light is off. Light is back on. Light is off. Light is back on. So when you toggle the switch going to the base, so let's play with this. Let's find the value at which the LED turns off, right? So let's increase the value of this resistor to 10K. It's still on. Now you see the voltage is changing, the value dropped, and the current is changing. When we have 1M, the light is dim. I don't know if you can see with the capture device, but the light is dim here, but it is still some current is flowing. 1 milliamp, 10 volts. So let's just decrease it gradually and see at what point we get it to light up. It's lighting brighter. So at 50 kilo ohm, so let's see. At 600 kilo, it's still lighting but not that bright. So you get a gist. So you can play this simulator. I recommend it. I don't have any I'm not sponsored by these people or the I think it's National Instrument or so. I stumbled upon the software and I felt it is cool. I normally do these kind of things with actual resistors and transistors and all that just to demonstrate. But I realized, hey, these people have already done a good work in giving us this online simulator. You can just use it, multisym.com/create, and you can just play around with it. And when you're done, you can build your circuit. You can, you can afford to fry your components here, and just nothing will happen actually. So this is it. So transistor is an electronic switch. So you can think of what you can use this for, right? So you can have a relay in this space and just use the switch to turn it on and off. And you can have, remember we talked about photodiode, you can have a photodiode here and have a relay here, or photoresistor. Actually, I didn't talk about photodiode, but that's one other thing. The diodes, you have the regular diode, rectifying diodes, Zener diodes, you have the LEDs, light emitting diodes, but you also have the photodiodes. They respond to light, like your operators, remote control sensors. They have the light emitting diode on one side, or infrared transmitter on one side, infrared receiver on the other end. So you can use diodes as you can have a photodiode right here or a photo resistor right here, or actually close the circuit and just have a photo transistor here. So the lights will control the current flowing through the base. So the lights will be the valve, and it will control when this comes on. So you can build an alarm. This is a simple circuit you can build easily. How many components here? 1, 2, 3, 4 components. So this will be your alarm, and you have a transistor and a resistor. It's an optional device. If you're using a relay here, please endeavor to put a capacitor around it. We're going to talk about it next in inductor. So let me just leave that for now. So this is what happens. You put a light emitting, a light sensitive component, yes. So light dependent resistor or photodiodes or phototransistors here, and as the day goes brighter or darker, the current will flow or reduce, and the maybe alarm will go off, or something will happen, an event will take place, right? So think about using this for a PNP transistor. So let's do that before we switch over to inductors. And I think that will be it for today. Once we cover inductors, then we can go in details in the future and talk about other components. Now, before I make a connection here, remember I said to have this in a forward bias direction for NPN transistors. So I'm going to go back. For NPN transistors, the collector must be positive, most positive, with respect to the base, with respect to the emitter, in that order. Collector must be most positive. What do you think will happen for PNP? Of course, collector will be the most negative. So the way it's pointing now, we can leave it. It doesn't matter. We can leave it, but we have to reverse the voltage, or we can reverse this, right? So let's reverse the voltage. So or we reverse this. Okay, let's reverse this. So we're gonna have it this way. And no, we don't need this here. We need the switch taken out, and we need it from this side. All right, we can get rid of this guy here. No, we don't need you out. We need the resistor out. And this switch we don't need. All right. I like to make things line up, but it's not necessary. This is a simulation, so it's not necessary. But it's just my preference to make things line up. So let's look at the circuit again. So we said for PNP, the emitter will be the most positive, and the base will be the mid, and then the collector will be the least positive. This is just a reverse of the PNP of the NPN transistor. So let's turn this off and then on. So I did it quickly because I'm already familiar with it, but I just demonstrated it to you. So you need the base to be as negative as possible, so you can actually ground it without the switch and the resistor. You can just draw it straight and ground it. But for this switch, you can use phototransistor, again photodiode, and so you can build a circuit that does something when the light is on, and another circuit that does the converse when the light is off. And you can use the same photo device, so diode, resistor, transistor, but you have to use a different configuration, right? So you can set up PNP and NPN transistor at the same time, and one will react this way under a condition, and the other one the other way under a different condition. So we're done with transistors. You might have other questions. We can use this as amplifiers, like I said. You can also, let's check the current flowing now. It's gonna be similar, right? So The only thing we change is the transistor, but the condition remains the same. All right. So when the switch is on, let's let the switch off. Get the switch on. So remember when we had a variable resistor circuit, you can put a variable resistor here and play around with it and see what value, just like we did here. We play around here and see at what value the light goes off. So you can use a variable resistor, to achieve the same thing, right? All right. So let's do that quickly. I'm doing all this to show you that nothing is impossible. Nothing is impossible for you. All right. Let's do this quickly. All right. All right. All right. This value allows us to have it on, but what if we go here and we want to change the value, right? Now let's just do the percentage. Yeah. So all the values here are within limits. It's just 10K. So let's increase the values. Let's go crazy. Let's make it 1M. All right. 1M. At some point we get the light to light on. 1M seems to be very high. So let's go down a little bit. Let's make it 100K. And then check the values. 100K seems to be within range. How about we change the value of the voltage here? Let's change this to maybe 9 volts. How about that? Let's do 9 volts first. 9 volts. And it's a little bit dimmer. But it's brighter when you have 0%. And 9 volts seems to be okay. Let's make it. Oh, sorry, I didn't mean to close that. I didn't mean to open that. Let's make the voltage 4.5. All right, 4.5 volts. And let's see what happens here. All right, 4.5 volts seems to be low. So we should be going for 6 volts then. Anyways, this is the luxury of using a simulation tool than building this practically. Can you imagine how many components you have to buy to verify all this? Yeah. So this can show is very bright here, and as you change the value, so this is assume this is daylight. It's brighter, is darker, is brighter, is darker, is brighter, is dark. When it's brighter, the value of the resistor is lower. When it's darker, the value is higher. You can use this for configuration for PNP and then use a different configuration for NPN. So let's look at one more component and we'll call it a day on basic electronics components. So again, I have all this in a book, detailed. Um, and everything was from a practical perspective. Remember, I was teaching students that are in their third year and fourth year and final years at the university, electronic students. So they are not lacking in the theories, but they needed some practical approach, and we're actually building circuits, transmitters and receivers and amplifiers and filtering circuits like we did, the rectifier circuit. We actually built it, not just explained it, but we built them, and some of them ended up building inverters and all kinds of circuits for other people, making money out of it. It's very great. It was really encouraging. So I'm gonna look at an inductor right now. Let's put a transformer here first, and then I'm not gonna connect it for now. I'll explain some things about inductor to you. So an inductor um, can store energy, right? It's an energy storage device just like a capacitor can. And when you use inductors in a circuit, this is very, very critical when you're using inductors, that you use inductors and make sure that you have. I'm trying to flip this component around, but it doesn't let me. So when you use inductors, make sure you have a diode across them if you're using it in conjunction with a transistor. Make sure you have a diode across them. You gotta make sure that you have a diode across them, and you have to use it in the right configuration, because if you don't, you might blow something in the circuit. um I'm not getting this to agree to flip. So something I'm not clicking on something. All right, so something is wrong. I'm trying to flip the component, but it's not flipping. So I'm gonna use it the way it's showing up, and we can just go with our experiment the way it is. So I need a power supply. Um, all right, and I need a ground. So if I have this circuit configured this way, um, okay, let's just add a switch. Again, single pole. Now let's run this. It's gonna complain about the component that we're not using. It's fine. Let's close this. All right. Did you see what I saw? All right. So there's 0 volts here. Zero. 0 volts here. Let's open this guy. The current is changing, but as soon as I close it, do you notice that it just goes and then it gets to a value? You know why? Why does it give me 0 volts here? Can you tell? Because I'm shorting this to ground. There's no voltage drop anywhere. So of course that's obvious. You will tell me that. That's obvious. You're measuring something from ground. Okay, let's put a resistor. Let's put a resistor. Okay, this circuit is zooming too much, so let's find a resistor that looks the way we want. We need this resistor, but none of them is allowing me to copy. Why? Did I exceed my quota? Now I can't copy. Okay, I'm just gonna put a resistor here. Mm, all right, so let's try it one more time. Ignore the complaints. All right, so I have 12 volt source, and right here it's measuring 12 volts because this is seen as an open circuit. The as a closed circuit, sorry, short circuit, just a piece of wire. However, when I use this in a with a transistor in combination with a transistor, I'm going to show you shortly. When you use this in combination with a transistor, once you cut off the supply, there's a huge amount of voltage that is built around here. So this coil, when current, remember, when current flows through a conductor, it creates a magnetic field around the conductor. Now, when the current source is removed, that magnetic field has to collapse. But do you know what happens when a conductor is brought into the presence of a changing magnetic field? What happens? There's an induction. So that collapsing current will induce voltage into the inductor wires, and that has to decay somewhere, has to go somewhere. And if it could damage the transistor in the circuit. So let's put a transistor here. Let's put a transistor and see if we can blow up one transistor. I don't know how this is gonna work with a simulator, but in real life, it's a dangerous situation. Let's see if we have one of the circuits that we did already, so we can reuse it, right? So we don't have to draw the circuit over. So here, instead of the LED, why don't we use an inductor? Yeah, so let's use an inductor here. Let's just go this way. What is it? We're gonna get rid of this resistor, we don't need it. Alright. Okay, so we don't have an LED, so it doesn't give us visibility, but we can look at the voltage across 6 volts, and the 6 volts is flowing here. When I open the circuit here, what can happen sometimes is that this can blow. So why don't I put, maybe I can put an LED somewhere here. But I'll show you the configuration first. Let me show you the configuration, how you take care of this. Um, let's go back. I'll stop this. Let's go back to the previous configuration, and I will show you how to protect your circuits. All right. So let's use right here. Instead of resistor, we use an inductor. All right. Okay. Okay, let's run this simulation again. All right, so close the circuit and the LED is on. Open it, close it, open it. So the configuration here, how you treat this is you have to put a diode across this inductor, and you put it in the reverse biased direction. So I'm gonna put a diode. I'm gonna flip it, not this way. All right, put the diode across. Where's the diode? Okay, I thought I exceeded the quota, but we didn't. All right. So here and then there. Then we can run the simulation one more time. Alright, so this is the configuration, so that when I open the circuit, any excessive voltage that's generated circulates around this diode and doesn't blow our transistor. It protects our transistor. I'm going to try to use the diode in the reverse direction here. A light emitting diode, sorry. Let's use a light emitting diode here instead. Let's see if it lights up, right? All right, we're gonna close the circuit. All right, current is flowing. Electromagnetic flux is built around this coil. When I remove the source, the flux is broken down and induces voltage around this coil, and that voltage circulates here until it decays. The amplitude starts high and quickly dies away. Okay, let's go a little bit crazy. Let's increase the voltage here. Okay, let's hope we didn't fry something. And you see, this switch is not really turning off power. This switch is turning up of current from the gate of this transistor. So let's close it and try to turn off the power instead. All right, we don't see anything going wrong here. Whoa, this is too high. Did you notice that? Did you notice what happened? So I did this on purpose to create an effect. If you notice when I turn off the switch here, the LED lights up because, and it's after the switch is off. When I put it on, it lights up momentarily. When I put it off again, it lights up again. Now, when I put it off, there's no reason to light up because why? The power is cut off. Where is it getting the power to light up? That's because voltage is built around this inductor. This is just 1 microhenry. I can increase the value to something higher, right? Voltage is built around this, and that voltage has to decay and go somewhere. And that voltage, if you don't have this configuration, it can blow your transistor. So let's do it again. When I put it on, you could argue maybe there's some jitters, that's why it lights up. But what happens when I put it off? Why does it light up at all? So let's increase this voltage a little bit more. We're going to do a little bit more experiment here. But this is even more crazy, right? We're going 1 point now. Okay. The moment the voltage increased, did you notice that it light up? So let's turn this off. Did you notice this is still on even though the power is off? Something is happening because this switch is probably not strong enough for this kind of voltage. The switch, even though it's open, is still allowing some voltage to go through. That's some stuff right there, right? So you can put some analyzers somewhere to find out where where the power is coming from. Let's put one here, voltage and current. Let's put one right here. We can figure out what is happening and why. Let's put one more current and voltage. Let's put one more right here. We're gonna find out what's going on there. So we have one there. Do we have everything captured? We need one over here. And that one is not necessary though, but we're gonna do it just to for completeness, right? Okay, we'll run it. Okay, what do you see? Right here, 1.2 megavolts, which is the full voltage. Of course, it makes sense because it's coming this way. How about the voltage at the base of the transistor? We're missing something. Let's find out voltage and current here. Save your design. Oh, something has crashed. Alright, something has crashed. We saved the design under a different name, but it's not even letting us get there. Okay, I guess this is it for today. Um, can we save the design with a different name while this is popping up? No, we can't. Alright, we can't do any more work today. Alright, did we fry something? Anyways, I can just explain to you manually what's going on. So when the voltage here, it's um okay. Let's try if I can recreate a circuit. It's gonna be a pain because I was gonna go back and show you other things, but it's okay. It's one of those things that It says I'm not logged in, so wasn't I logged in? Was I logged in or not? So doesn't matter. Let's recreate a circuit. It's our design, so we can make it look the way we want. We need an inductor, right? And okay, we need an inductor. We need a power supply. We need a ground. Sometimes people call it S. I'm not about semantics. I'm about making it work. If it works, it works. That's my theory. Some people are maybe it's the sticklers for the right name, if it's ground or earth. Some people say chassis sometimes, depending on what they're working on. But if you get a concept, you got a concept. That's what I'm about. I want you to get the right concepts, and you can make your own circuits. I teach my students to be able to understand. Understanding is principle is core for me. It's very, very important to have the understanding of what you're doing. Once you have the understanding how you do it, you can do it in a million and one ways. Doesn't matter. All right, I think we've recreated the circuit. We just need the reverse uh, component. Yeah. So it's good we didn't waste a lot of time trying to fix what was broken. We just recreated it. All right. We can adjust the rest once we start. So we need a source here. We need to analyze what's going on here. We're gonna analyze what's going on there. Also, you want to analyze what's going on here. This you already know, but we are seeing a strange behavior, right? We're seeing a strange behavior where the LED is lighting up when the power is already switched off. So it's a strange behavior for us, right? So we want to figure out what's going on. So let's close the circuit first. Close this. Oh no, we need to make sure this is connecting, otherwise it won't perform any analysis. All right. So here we have 12 volts. Now we already know from the previous video before the crash, we need a very high voltage to get this to misbehave. Right. So um right here this LED is on. Why? Why so? The base of the transistor has enough voltage to light it up. For an NPN transistor, you need at least 0.6 volts, about 0.7 volts, 0.65 or so for a silicon transistor. For a germanium transistor, you need about 0.3, 0.25, 0.3 volts or so to light it up. For a diode, if it's silicon, the forward voltage drop is about 0.6, 0.7, and for germanium is about 0.25, 0.3. And even there are Schottky diodes and the rest of them, they even go even lower. The voltage drop across them, or for the forward bias voltage drop. Now, so we can see this transistor is switching on because it's all it needs is about 0.7 volts, and it's getting it from somewhere because the switch, even though the switch is open, because of the amount of voltage there, there's an induction, the voltage is creeping across. Voltage is creeping across. It's showing 12 volts creeping across from air. So when you're using certain amount of volts, so let's lower this voltage and see how the voltage is going to drop. Just watch this voltage drop from 12 volts to something lower. I'm going to drop it by 10. It drops to 2 volts. And still I have enough because I have 800 millivolts. It's still enough to turn this transistor on. So let's Let's go gradually this time because 800 is just so close to 7. Let's find out what value at which it will turn off. Oh, okay. Now at this point it's too low. When did we get so at what value of voltage? Oh, it's 0 volts. No, I don't want 0 volts. I want a little decrease, not 0 volts. Where's the 0 volts? Okay, let's just make it 12 volts and see. At 12 volts, it's not big enough to cross the boundary. Let's make it 15 volts. At 15 volts, still not enough. How about 20 volts? At 20 volts, still not enough. How about let's just go up gradually. 20. We're looking for this value to get to 0.7 or 700 millivolts. So let's see what value gives us 700. We are getting close. We are getting so close. We're getting so close. Yep, right. So this transistor should be on around this time, but the voltage is not crossing enough. Let's see. The transistor is not coming on because basically it's still open. So I guess we have to have a very high voltage before we can turn the transistor this circuit on. But anyways, let's go. What we're looking for actually is 1.2 like we did previously. 10 volts. Let's just make it high. 100 M is too high. 1 M. Okay, let's go 1.2. So we have the same value as before the crash. All right, so this is where we were. Now we saw that as the voltage increases, this value increases, and then this transistor starts to conduct. But anyways, I'm going to close this circuit, make sure it is actually on. But you notice the moment I put it on, this second LED comes on. Should not. Why? Because it's reverse, and this voltage is in the forward bias direction. So it's reverse. No need, no reason this transistor, this LED should come on. No reason. And when I turn the power off, it is after I turn it off, you see it stays on for a couple of seconds. Did you notice that? Did you notice that? When I turn it off, it's for a few seconds. The power here, the voltage here is decaying. When I close it, there's an induction that happens on this point. And that induction also it's creates some reverse voltage to flow. And when I turn it, when I open it, you know what? Just something just came to my mind. Why don't we add one more LED right here, right? Why not? I mean, why not? So I'm gonna add it. I'm gonna make 2 of them. All right, we're gonna run this one more time. This inductor is becoming more interesting than I initially thought. I was just gonna show you quickly an inductor and then probably do step up transformer and step down transformer, but we might not get to that today because of the amount of information we're getting here. So in the forward direction, this LED is on, which is fine. This is also on. So, but when I turn off power, what happens? When we turn off power, all of them are on. There's no power. How could this be? Okay, there's time too small, trouble, unable to so there's a crash, there's a problem. Okay. I see the simulator just froze because there was a problem. Um alright. When I close it, this lighted up briefly. When I open it, yeah, this lighted up briefly and cut off. And these two stayed on because there's a phantom voltage going through the switch and causing these transistors to stay on. Okay, so this is interesting, guys. This is interesting. I'm going to reduce this voltage in the realm of something that makes sense. We don't really think this is possible. Let's do it 12 volts. Having 1.5 uh 1.2 megavolts is asking too much, to be frank. And please don't handle such voltage on your own. You're gonna injure yourself. So we're just gonna increase it gradually until we can get enough that can light this up in the reverse direction. Anyways, you have seen that this can happen. You can actually get voltage to flow in the reverse direction um, when you have an inductor in a circuit and the circuit is broken down. You know the power is removed. So just watch. I have 120k volts. When I open it, it creates voltage here. So and this is what you can see, the amount of voltage that you can see, but sometimes you can't see it. And sometimes the value of this current or voltage that is developed is also dependent on the value of the inductor. So here we are using only 1 microhenry. How about if we use much higher? Let's use 1 amp, right? What if we use 1 amp? See, the decay is longer. It's still on, the power is out. It's still on, it's decaying gradually. So the value of the inductor will determine how much. Remember I said inductors are used for energy storage. Think about how you can use these inductors to store energy. So even though power is out, it's very, very dangerous. Now, if you're working on TVs, you probably know this already. You know the um, inside, if you're using a CRT, cathode ray tube, so they have the yoke that is connected to the you have the line transformer kind of that's connected to the yoke. Maybe not the yoke, but the CRT itself. I forgot the name of that. So it has like maybe 32,000 volts or 22,000 volts. And even when your TV is off, the capacitor is storing some voltage, the inductor is storing some voltage, and it could electrocute someone if you're not careful around it. We've just seen here, circuit is open, and yet the voltage stored or developed because of the 100 millihenry inductor is still here decaying, and it's going to take a while to end. So why don't we just reduce the value? This is actually one microhenry, 1 microhenry, 1 millihenry, sorry, and then 100 micro, 10 micro. Let's keep it at 100 micro. I'll try one more time. Let's 100 micro. Let's try one more time. Close. It stays on for a while. Open. Stays on for a while. It's gonna decay faster, but it stayed on for a while. This tells you what I'm talking about. So I can even reduce this voltage now in the realm of what makes sense, 12 volts, and just increase the inductor value. And you see, oh, this is 12 kilovolts. Okay. So how about if we increase the value even more? 1 Henry. Oh, whoa, 1 Henry. Is that ever gonna go off? Okay, how about we'll decrease the voltage here to something. Let's do 12 volts. most likely what you can see in real life will be something in the realm of 12 volts. Well, hey, the voltage was stored from last time. It's still present. Okay, so let's run the simulation afresh. All right, turn off, and it's still on. So in real life, in real situation, you're gonna see up to 12 volts or even more in some circuits. But if the inductance value is high, you're gonna see this voltage develops that has to decay and go somewhere. Now it's gone. Right, let's start again and see the value. All right. So I'm gonna open it. You can see it starts 1 point something volts here, 500 millivolts, and then it goes all the way to about 500 millivolts, and then the LED goes off. Okay. All right. So this will be it for inductors. So when you build a circuit that you have an inductor in it, if you have a transistor as a switch driving an inductor, make sure you have uh, a diode connected in the reverse direction, so it doesn't, because if it's in the forward direction the voltage will flow through your transistor and could damage your transistor. So we're just gonna flip that now, and we do that experiment, and then we can call it a day. Duplicate, and then flip it, and then we'll delete this one here, and we put another one there. All right, let's run this. So this probably might work, but there's just a danger. The current will flow this way, and if it's high enough, will flow through your transistor. So let's just go crazy like we did before. Let's start from 120k red and see if we can blow the transistor. Yeah, this transistor is almost on. This LED is almost on. So let's increase the value of this voltage one more time and see what we can break. I think we probably broke something already. Unable to do coverage, converge, con, converge, unable to converge. Okay, let's go down a little bit. Are we able to converge now? Okay, we're able to converge now. So let's open it. You can see this is a little bit bright. When I turn it off, watch this too. They're still on. This is already off. Okay, so just bleeding or leaking. Anyways, that's all I want to show you today about inductors.